Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week. And again, the topic comes from one of my subscribers, and they wanted to know, why do we have more hail in the spring than we do in the winter? Which is a reasonable question, and because you might be thinking, well, if it's colder in the winter, wouldn't we have more objects made of ice falling from the sky? So there is a good reason why hail is more favored in the spring than the winter. And I'm actually going to talk about a few related topics, and you might think early on in this video that, hey, wait a minute, he's not talking about what he said he was going to talk about, but I will try to tie it all together at the end, okay? But some of these definitions I hope will be helpful in understanding some of the concepts that relate to the production of hail. So let me go on ahead and put myself down here in the corner, and let's talk about some definitions. So the wet bulb temperature is the temperature at which the air would fall to if it became saturated via precipitation falling into it. I don't know how many of you remember this or ever did this back in your school days, especially you old timers like me, where there was something called a sling psychrometer, and it had two thermometers on it. One was called a dry bulb thermometer, which was simply measured the air temperature. But then the other one, you took a little piece of saturated wet cloth and secured it as best you could to the bulb of the thermometer, and then you would swing this thing as fast as you could. And the fact that you were swinging it and it was moving through the air meant that you were going to get evaporation of water from that cloth. And evaporation is a cooling process. If you don't believe that, the next time you jump out of the pool or the shower and you feel cold, that's what's going on there. Evaporation is extracting heat from the air around you, and so you end up feeling cool. But in any event, when you can't get that wet bulb thermometer to go any lower by swinging it, that is the wet bulb temperature. That's the temperature at which the temperature and the dew point will converge. So when precipitation falls into dry air, the dew point will rise because you're adding moisture to the air, and the temperature will fall due to the process of evaporation that is extracting heat from the air. So when the temperature and dew point meet, then that means the air is saturated. Now, sometimes you can estimate the wet bulb temperature by taking the average of the temperature and the dew point, but that only works in certain temperature ranges, and I'll talk more about that in a little bit. Now, there's also something called the wet bulb zero height, and that is the height at which the wet bulb temperature is at 32 degrees Fahrenheit or 0 degrees Celsius. And it has been shown that for significant hail, large hail, that the wet bulb zero height needs to be, on average, between 7,000 feet above the ground and 10,500 feet above the ground, okay? And again, there are reasons for that, which I'll get into in just a little bit. So let's take an example here where the temperature is always 20 degrees higher than the dew point, okay? So you got 20, 0, 30, 10, all the way up to 180, or 180. And there's also something called the mixing ratio, which is defined as the number of grams of water vapor per kilograms of dry air. And what I want you to notice here is that as the dew point goes up 10, then this is the amount that the mixing ratio is going up. Here it goes up another 10, the increase is bigger, another 10, the increase is bigger. So the amount of water vapor in the air is increasing exponentially as the dew point goes up by the same interval, okay? So if I want to show that to you graphically, it looks like this. The dew point's along the x-axis, the mixing ratio along the y-axis, and so as the dew point increases, the mixing ratio increases not at a linear rate, and if it did, that would be a straight line, but a curved line like that means it's actually increasing exponentially. So the higher the dew point, not only is the amount of water vapor in the air increasing, but it's increasing by a greater amount for every 10 degrees that you continue to go up. Now, in terms of the wet bulb temperature itself, let's take our same examples here where the temperature and the dew point are 20 degrees apart. Now notice at 20, the wet bulb temperature is actually much closer to the temperature, and that's because there's so little water vapor in the air at those temperatures that evaporation is not a really effective process, okay? And so the wet bulb temperature is skewed toward the temperature. But when you get to about 60, okay, 60 with a dew point of 40, the wet bulb is right in the middle. And that's what I was talking about earlier, where there are certain temperature ranges where you can take the average of the temperature and dew point and estimate the wet bulb. Even around the freezing mark, it's not that far away. Like if you're 40 with a dew point of 20, your wet bulb is 32, which isn't that far away from the middle of that range. Then you get up here and you have a temperature of 100 and a dew point of 80, and by the way, I would never recommend voluntarily subjecting myself to that kind of air. The wet bulb temperature now is closer to the dew point because there is so much water vapor in the air that the evaporation process is very effective, and so it tends to skew the wet bulb temperature toward the dew point as opposed to the temperature. So you can see that here at 20, the temperature decreases only 5, the dew point increases 15, exactly the opposite at 100, the temperature decreases 15, and the dew point only increases 5. So, last thing I wanted to show you, this is off the Storm Prediction Center climatology site, sounding climatology site, and this goes from January to January, and this is what's called the significant hail parameter. And so you can see here that this peaks right around June 1st, and you could probably go a couple of months either side of that. But if you look at all the hail observations of all sizes, it actually peaks here in the middle of the summer, which you might find a little bit interesting in the sense that that's the warmest part of the year. But you get air that can be very, very unstable. In other words, an air parcel begins to rise and it's very buoyant and it's accelerating upward and it gets way up into the cold part of the cloud, and you have hailstones that grow at the expense of supercooled water droplets around them, and when they get big enough, they fall. But again, this is all hail observations here. The significant one actually peaks earlier. So what is the significance about the 7,000 and the 10,500 as being that sweet spot? Well, if the wet bulb zero height is less than 7,000, it generally means that the air is cold and is probably stable. It's going to be pretty difficult to get an air parcel to become buoyant and to accelerate upward when it is at the coldest time of the year, okay? So you can get sleet, which is an entirely different process from hail, but getting an accelerating updraft that is going to get up to the point where it can produce hail, that's tough, in the coldest part of the year. Now, if it gets above 10,500 feet, then the problem is that the atmosphere is so warm as a whole that any hailstones way up there are probably going to melt before they get to the ground, or at least mostly melt by the time they hit to the ground, because they've got such a great depth of above freezing air to fall through. And so you want the atmosphere to be warm enough so that it can become unstable and you can get these updrafts that are accelerating, but you don't want it so warm, okay, that there's simply too much warm air above freezing air for the hailstone to fall through, and so it melts long before it actually gets to the ground. So that 7,000 to 10,500 is the sweet spot for large hail. In terms of regular hail, pea-sized hail, whatever, that can occur at just about any time of the year. But as you can see here, it actually occurs overall with all sizes of hail during the middle of the summer, okay, which is ironic. But the reason that the large hail is skewed earlier is that the overall atmosphere is still cool enough to produce the large hail. Once you get over in here, I'm sure the predominance of reports are hailstones that are pretty small. Okay, I hope I did a decent job of explaining that. I'm not sure that I did. But if you have anything you need clarified, post it in the comments below and I will do my best to clarify those points for you. It can get a little complicated, but we can work this out. So if there's anything that doesn't make sense, let me know and I'll try to respond to it as best I can. All right, that is bonus weather video number 1 for this week. There are the credits. The next bonus weather video will be coming up on Wednesday. Next daily weather update coming up tomorrow. So I hope you have a really, really nice Monday evening, and we'll talk to you again tomorrow. See you later, everybody.